In this lesson, we're going to be factoring with special patterns, and once you can recognize these patterns, it makes factoring these special types of problems a lot quicker and easier. So before we get started, we're going to talk about, describe, or explain what a perfect square is. So we've already talked about perfect squares in the context of simplifying radicals. They are those numbers that have a square root that's an integer. And so what makes them that way? So you might describe a perfect square as a quantity squared or a number squared. For example, 3 squared equals 9. But why are we calling it a square and what makes it perfect? So 9 is a perfect square because it's a number times itself. And also if we literally had something that made like you have 3 units here, 1, 2, 3, and you have 3 units here, 1, 2, 3, and when you multiply the 3 by 3, you get a box of 9, and it forms a perfect square. So a number times itself, or a number squared, creates the perfect square result. So the 9 is the perfect square, just like in the image, the 9 squares form a perfect square. So the question then is, can variables be perfect squares? So could we create a perfect square situation out of variables? And yes, the answer is yes, we can multiply a variable times itself. So for example, x squared is a perfect square. So a perfect square is a number or variable expression with 2 identical factors. We have these 4 examples down below, and we're going to double distribute to simplify and eliminate the parentheses. So on this first pair of binomial factors, we'll multiply x times x will give us x squared, then x times 8 gives us positive 8x. Here we have 8 times x, that gives us 8x again, and 8 times 8 is 64. Then we can combine like terms here to get x squared plus 16x plus 64. Now this next one, it's almost exactly the same, but we can't expect the exact same outcome here because we have a different sign in our second quantity. So we'll do the same thing again. X times x is x squared. X times negative 8 is negative 8x. 8 times x is positive 8x, and 8 times negative 8 is negative 64. Here, when I go to combine like terms, I have opposite signs, and these 2 x terms eliminate one another. Negative 8x and positive 8x gives us a 0 sum in the middle. So now we have x squared minus 64. On this next one down here, we have x times x is x squared. X times negative 5 is negative 5x. Here we have negative 5 times x again, and positive 25. When I go to combine like terms here, same sign, so we're going to add them together to get negative 10x. So we have x squared minus 10x plus 25. And then finally this last one, so x times x gives us x squared. X times 5 gives us positive 5x. Here we get negative 5x, and then negative times positive gives me negative 25. Here, my 2 like terms in the middle, I got a positive 5 and a negative 5. Again, those eliminate each other because they have opposite signs, and our sum is actually 0x. So we end up with x squared minus 25. And our middle term, that's called the linear term, is 0. So what patterns do we notice? There are a couple things that are happening here. One thing is that we've established some perfect squares. So if we look at the constant at the end of the expression, here we had 8 times 8, and we ended up with 64. Here we had 8 times negative 8, and we had negative 64. So the 8 times 8 is a perfect square. But then if you put a negative with it, it turns your product into a negative result. And then down here, similarly, we have a negative 5 times negative 5, that's positive 25, a perfect square. and then we have negative 5 times 5, which gives us negative 25. We also have another thing, which is that here where the signs were the same, so I had positive and positive, I ended up with positive 8x and positive 8x, and those combined to give me double the number that was in the parentheses. So I had 8 in the parentheses, and I had 16x for my linear term. And then here, in this one, I had a negative and a negative. That gave me negative 5x and negative 5x, which combined to give me negative 10x, or double what was in the parentheses originally. And so if we have the same sign in here, we end up with a positive perfect square constant, and we end up with two matching middle terms that combine together. Now over here we had opposite signs. So one positive and one negative. One negative and one positive. So what happened here was when we added our two linear terms, they had opposite signs, they eliminated one another. And the same thing happened down here. And when we multiplied the negative times the positive for our perfect square, the result was always negative versus over here it was always positive. You may have also noticed that these are the same factor twice. So this could be rewritten as x plus 8 quantity squared or x minus 5 quantity squared. So maybe we can apply the pattern that we see here to a problem with different numbers. So what if I had x plus 2 quantity squared? We should expect to get x squared for our first term. We should expect to get double this number for our middle term. So 2x and then another 2x would give us positive 4x. And then for our last term, we should end up with 2 times 2, or 2 squared, which is also 4. So this is what's known as a perfect square trinomial. Over here, what you may have noticed is that you have the same two terms but with opposite signs. And what we expect to happen is that the two linear terms drop out and the last term, or constant, is the perfect square of the two numbers but with a negative. So for example, if I was doing x plus 7 times x minus 7, I know my first term should be x times x, which is x squared. The outer term is going to be negative 7, and the inner term is going to be positive 7, which I know are going to eliminate one another. And then 7 times negative 7 is negative 49. This is a difference of squares. In recognizing those special patterns of multiplication, we can also apply them in order to factor. So first we'll talk about perfect square trinomials. In a perfect square trinomial, you will see 3 terms, so the expression has 3 terms. The first and the last term are perfect squares. And it may be a perfect square involving variables or integers. But the first and last term will be perfect squares. And then the middle term fits the pattern of 2ab or negative 2ab. So if you look down below here, I have an example with just variables. And so my first term, whether it's x squared, a squared, 4x to the 4th, could be anything, but it has to be able to be split into 2 identical factors. Remember, we talked about the definition of a perfect square could be described as having 2 identical factors. So a squared could be split into a times a, those are identical factors. B squared could be split into b times b, those are identical factors. So both the first and the last term are perfect squares. And then in the middle, this just kind of helps me visualize it. I think of each of these pairs of matching factors being multiplied by their bookend on the other end. So this would give me AB, and then this would give me AB, and when I add those together, I get 2AB. So it fits this pattern of the perfect square trinomial. When this occurs, we can factor it into 2 identical binomial factors. And so over here, if I was referring back to this same one, if it's a squared plus 2ab plus b squared, then I should expect the two identical binomial factors to be a plus b and a plus b. Again, they're going to be matching, and we could rewrite this as a plus b quantity squared. Now, if this is negative, then that means that both of these factors in here would have to be negative instead of positive, and so both of your signs will be negative inside your parentheses. So this would just be a minus b times a minus b, or a minus b quantity squared. So that's the pattern for a perfect square trinomial. And we have a few examples of these down below. Let's analyze example 3a. I could split x squared into x times x, so that's a perfect square. And I can split 9 into two matching factors of 3 times 3. If I took 3x and 3x and added them together, I would indeed get 6x. 3x and 3x does add up to 6x. So this does fit the pattern of a perfect square trinomial. And so therefore, I can factor it using this shortcut, x plus 3 quantity squared. All right, let's look at b. Again, we have x times x, and we have 10 times 10, 10 times 10. And if I put these together, that gives me 10x and another 10x. Well, here's a problem. I have a negative here, so both of these would need to be negative, which means that both of these factors would also need to be negative. Negative times negative is still positive. So this is still a perfect square trinomial, but it'll be x minus 10 quantity squared. Ultimately, the sign in your parentheses will match the sign of the linear term. So here we had positive and here we had negative. Let's try C. 36x squared, that's a little bit different. We haven't had one with a leading coefficient other than 1 yet. But how could I split 36x squared into two matching factors? 36 is a perfect square number. So if I wanted to split 36 into two matching factors, that would be 6x times 6x. Okay, so what about 1? We could split that into 1 times 1. And then 6x times 1 is 6x, and another 6x times 1 is 6x, and we need a negative in the middle. So our quantity squared will be 6x minus 1 quantity squared. We have 4x squared. We could split that into 2x times 2x. 25 we can split into 5 times 5. 2x times 5 is 10x. 10x and another 10x would give us 20x. So that fits the pattern as well. That'll be 2x plus 5 quantity squared. Now, if I wanted to do these the same way we've been doing all the problems we've been factoring so far, we could. So we've learned guess and check, slide and divide, sum and product patterns, and those will all still apply. But if you can recognize that the perfect square trinomial pattern exists, then you can get really quickly to the correct answer without having to do any other steps. We will also use the perfect square trinomial pattern to complete the square in a later lesson in this unit. Now let's check out the difference of squares pattern. So you're going to have two perfect square terms. So your first term here would be a times a. That's two identical factors, a times a. And then your second term, b times b. Again, two identical factors. And you have those two terms being subtracted. So that means it is a difference of two squares. In this case, you will be able to factor this to a plus b times a minus b. And because you have these opposite signs here, when you multiply the outer term and the inner term and combine those two terms together, they're opposite, and they eliminate one another. So the expression will have two terms instead of three. The terms are being subtracted, and each term is a perfect square. So let's check it out. Here I have x times x, and I have 2 times 2. Of course, one of those 2's is going to be negative to give me that negative product, And so that's going to be x plus 2 times x minus 2. Next, we have x times x again, and we have 11 times 11. One of those is going to be negative to give me x plus 11 and x minus 11. Now down here we have a leading coefficient of 25, but I can split 25x squared into two matching factors. That'll be 5x times 5x. And then 16 is a perfect square of 4 times 4, and again, these are being subtracted. And so this is a difference of squares pattern as well. So our two factors will be 5x plus 4 and 5x minus 4. It doesn't matter whether you put the positive factor at the front or the back. Order doesn't matter because multiplication is commutative. All right, last one in this group, we have 64x squared minus 1. 64x squared, I could split into two matching factors of 8x times 8x, and then 1, we can split into 1 times 1. And again, we got to have opposite signs here, so 8x plus 1 times 8x minus 1. My little floating head is in the way. All right, so let's check out the bottom of the page. We're almost done. The last couple of problems are a little bit unique. This one is reversed, but we don't want to rewrite it with a negative leading coefficient. We're just going to put them in reverse order. So my first term is 6 times 6, and my second term is x times x. And so we can rewrite this as 6 plus x times 6 minus x. And then finally here we have one with a GCF. So always look for a GCF first in any factoring problem. So we can divide both of these by 2. So we'll bring out a GCF of 2. So we'll have inside our parentheses x squared minus 81. And then we'll continue factoring what's inside here, leaving the greatest common factor on the outside. So here we've got x times x and 9 times 9. So on the outside we'll have the 2, and then we'll break this down into two binomial factors, x plus 9 times x minus 9. So factoring with special patterns offers you a shortcut that can allow you to go straight from the problem to the answer if you recognize that the problem fits the pattern. Occasionally you will see a problem, well, frequently you'll see a problem that doesn't fit the pattern. And so I'm going to give you a couple of examples of those, and then you'll be ready to practice on your own. Here are a few practice problems for you to try. So if you want to pause the video and test your skills, you can do that. And then we'll come back together and see how you did. All right. So this first one, x times x, 7 times 7, you should have x plus 7 times x minus 7. Here, x plus 4 and x minus 4. And then finally, this one cannot be factored because it's not a difference of squares, it's a sum. So if I tried to factor this to be x plus 5 times x minus 5, 5 times negative 5 should give me a negative 25, and that can't work here. Well, what if I try x plus 5 times x plus 5? So this one did not work. What if I do positive 5 and positive 5? Then I would get, on the outside, I'd get 5x, and on the inside, I'd get 5x, and that would add up to 10x in the middle. And the same thing if I had two of these with the same negative sign. Then this would create, both of these would create perfect square trinomials. So these will not work either. So this sum of two squares cannot be factored. So this is prime. It has to be a difference of squares in order to be factored. All right, over here, your perfect square trinomials. This was a trick question because if I split this into 10 and 10, that doesn't add up to 52, that adds up to 20. So this is a problem that I cannot use a perfect square trinomial pattern, but we could factor this, x plus 50 and x plus 2. 50 times 2 is 100, and 50 plus 2 is 52, but not a perfect square trinomial. This one, you've got 9 times 9, that's a perfect square. You've got x times x, that's a perfect square. 9x plus 9x is 18x, so this does fit the pattern, x plus 9 quantity squared. And then finally here we've got 8x times 8x, and we've got 5 times 5. 5 times 8 is 40, and 2 of those would give us 80, so that fits the pattern as well. 8x plus 5, quantity squared. So I hope now you feel confident enough to practice using these perfect square patterns in your factoring practice. Good luck.